Chapter 16 in the physics book, Thermodynamic Laws. Now in this first section, we're just going to talk about an intro and the zeroth and the first law. And of course, I'll get to the zeroth in a minute. It's kind of funny, actually, the way it came about. But just like mechanical energy, thermal energy, help if I spelled it right. Sorry about that. Thermal energy has potential and kinetic energy. Remember we talked about that if an object is falling at its very peak, it has potential, but if it's still, no kinetic. And then by the time it hits the ground, that split second before it hits the ground, it has no potential, but it has kinetic. Well, with thermal energy, it does the same thing. You've got potential energy that is in the form of latent heat or latent heat. I've warned you that I mispronounce things all the time. It comes from being a math background rather than a science. But anyway, that's potential heat because as a substance approaches melting or approaches freezing, at those points, when it approaches freezing, it's going to give off heat as it freezes. And so that's why it's called potential. Now, the kinetic, that is just like the kinetic theory of matter. You know, things are always in motion. And so that has to do, actually not, thermal or its actual temperature has to do with the kinetics. So how warm or how hot the substance is has to do with the kinetic, because that's what the temperature relies on, is how fast those molecules are going. Just a vocab word, if you take the sum of the kinetic and potential energy of an object and you add it together, you just get its internal energy. So just to throw that out there, just a vocab word. Now, the first law is the one, an interesting fact, it is the law that is most thoroughly tested and confirmed in the entire physical science community. So it is guaranteed as much as human possible to be true. And the first law of thermodynamics is energy cannot be created or destroyed. In other words, let me write this real quick. In other words, hopefully that didn't go off. In other words, what goes in must come out. It might be lost to whether it's heat or friction or sound, but it's not that the energy is destroyed, it's just converted to something else. Now, as they were doing this, they noticed, and this is where the zeroth law comes in, actually, they had already come up with at least the first law, if not the second and third had discovered or known about them. They noticed, let's say that I have an object, and I have three different sections, A, B, and C. Well, they noticed that if A and B are at the same temperature, and if B and C are at the same temperature, and then A and C will be at the same temperature, as long as these walls right here and right here were diathermic. In other words, it's like a diathermic wall is a perfect conductor. In other words, the energy can be transferred from one side to another without any issues. Now, the total opposite of that is an adiabatic container that, in a sense, it's the perfect insulator because it allows nothing to transfer. Now, remember, last chapter we talked about adiabatic containers, and that kind of like a real life example of one would be like a cooler. It's a cooler allows some, but it reduces the amount of heat that's lost. And so the zeroth law, and why it came up to be zeroth, is because, well, they were like, that's too easy, that's too basic, and it can't come after the first law, so we'll just make it the zeroth law. And so they did. And so basically in math, it compares to the transitive property. If A and B are at thermal equilibrium, and that is just fancy science language for same temp. So if A and B are at thermal equilibrium, and B and C are at thermal equilibrium, therefore A and C are at thermal equilibrium. So that is the zeroth law. And as far as just a couple of vocab words, we'll need one of them here in a second. Systems versus surroundings. A system is just some piece or some isolated piece of the universe that science or the group is using to study. That's a piece of the universe. Surroundings are everything outside the system. Okay, good. You can't see that. Now, they also, as far as systems, there's 3 different types of thermodynamic systems. There's open, closed, and isolated. Now, an open system allows energy and matter to be transferred. Like, for instance, if you had the ground outside. If you had an object like a cup of coffee, or a bad example, we'll say literally the dirt on the ground. That's an open system because heat can be transferred back and forth. The sand on the beach. In other words, there's no container to separate it, so the matter can go back and forth. Energy can go back and forth. Now, a closed system, it doesn't allow matter to cross, but only energy. So a closed system would be things like, I'll go back to the coffee mug. The coffee mug the mug itself keeps the coffee and its surroundings separate, but if you've ever felt a coffee mug, you can feel the heat on it because the heat it's losing its heat. That's why on a Yeti container that you can't feel the temperature change as much, because it's a better insulator than just a regular coffee mug. A closed container, it can even have a lid on there, and it's still open, or as far as like a lid or not, it's still considered closed, because unless you spill it, the matter can't be transferred. Another example of open would be like a drop of water on the desk, because it can go back and forth. Isolated, nothing can be transferred, heat or energy. And the only time that happens is in an adiabatic container. Is there 2 R's? I think so. And last but not least, really quickly, because I know this one's going long, there are 4 thermodynamic processes. And the good thing is they're easy to remember by their prefixes. Now, thermodynamic process is just, I almost forgot a vocab word. A heat engine is just a device that allows you to use energy to do work. And we'll get a lot more on that in the second and third law, which is the next video. But it allows work by either absorbing the heat or discharging the heat. So going back either way is how the heat engine works. Now, the 4 thermodynamic processes, there's isothermic, isobaric, isochoric, we'll just say that's the way you pronounce it. As long as you can spell it, you're good. And adiabatic. And in each of these processes, something remains constant. Now, because iso prefix means same. So thermic, guess what's going to stay the same on this one? Temperature is constant. Isobaric, yep, you got it. Pressure's constant. Isochoric, well, this one you can think, oh, gas laws, PVT, volume constant. And the adiabatic container, since nothing is being transferred, thermal energy remains constant. Sorry that one went a little long. Hope this was of help to you. See you in the next half of the chapter video.